Good afternoon, everybody. Today I will present about fatigue of metallic classes, especially with one overload. Actually, the results I will show happened randomly while we were measuring K1C values on the metallic classes, but we thought it's very interesting. And so we want to compare the behavior with the overload effect of typical metals. So I will first a little bit present about the overload effect of the metals. So if we are measuring the A over the N diagrams for lifetime predictions, typically we do this with constant amplitude loading, then it looks very smooth like this. And here we have the Paris regime, and with the Paris equation, then we can calculate the lifetime till failure, at least for long tracks. That's okay, but in reality, the load spectrum looks more like this. PhD student of mine was collecting this during a bike ride, and so it's very different. And this also changes the complete crack propagation behavior. And the first step to get an idea how this changes is including one overload here in the constant amplitude loading. And this is what we started with. And if you do so and make this in situ in the scanning electron microscope, then here you see the normal fatigue loading. Maybe you can see some plasticity in front of the crack, even here at this position. And now if you make an overload, 50% overload, then you have a huge plastic zone in front of the crack tip. You have huge plasticity here. And if you increase the overload, then it looks like this. In this case, the material was not a metallic glass. This was a low alloy high-strength steel. And what you can do is you can make digital image correlation by this, or you can perform other techniques to get an idea about the deformation zone or the residual stress zone in front of the crack tip. And in our case, we measured this here with Barkhausen noise. By this, you get the residual stresses in front of the crack tip. This here is before the overload. You see a small plastic zone with residual compressive stresses. After the overload, you have a really big zone with compressive residual stresses, and then the crack is growing through this zone with these compressive stresses. And here it's called maximum retardation, and this is prior speed. What do I mean with maximum retardation? If we go to our dA over the N diagram, it looks now like this. Here, this would be the Paris regime without an overload, and after the overload, the crack propagation rate decreases. It's a really huge decrease. And after 50, 100, and 150% overload, as you see here, so the effect gets stronger with higher overloads. And now this makes lifetime prediction quite complex if you do not have a constant amplitude loading. And if you calculate or if you measure the crack length as a function of the number of cycles, then it looks like this. Maybe if you would just extrapolate the normal fatigue crack behavior, it would go here in this direction. And if you think 1.5 millimeter is the final crack length, then you increase by the overload your lifetime from 25,000 cycles to 50,000 cycles by 50% overload, up to nearly 150,000 cycles by 150% overload in this case. So this is the overload effect, and there are several ideas where it is coming from. One is that we have plasticity-induced crack closure, which means that the crack is closed by unloading. So the effective delta K is only here reached in this area of the loading. And the other thing is that we have the residual stresses in front of our crack, which will reduce the maximum load. And this again reduces then our effective stress intensity factor, cyclic stress intensity factor. And this means that the local K and the applied K should look like this. You have delayed opening and decreased maximum local K factor. And if you are measuring this just after the overload, you see no difference. And this is exactly what you have here in the diagram. Here, somewhere here is the overload, and then it takes some time for the crack to decelerate. And this is what you see here. And at the point of maximum retardation, it looks like this. It looks like here in this diagram. So now we come to the metallic classes, and the question is, what is different? If you search for fatigue and overload in metallic classes, for fatigue, you find more than in metallic classes nearly 2,500 papers. But if you are adding overload, you get 4 papers about this effect. So it's not very often investigated so far. And if you look in Wikipedia for metallic class WIT 105, then you will find that the first commercial use was in golf clubs in the club phase, and the prototypes shattered after fewer than 40 hits. And this means you have a low cycle fatigue problem, and you will not have a constant amplitude loading in this case. So the first goal was we want to measure K1C and DA after over the N while we initiate the crack for the K1C measurements. The specimens were small CT specimens. See here, the width is 12 millimeters of the specimens in total. And we had as notch, a chevron notch, here a shallow guide side notch to lead the crack, the fatigue crack growing in this direction. And then during the initiation of one of our fatigue cracks, an overload happened due to a regulation error of our loading machine. This here is this loading machine, servo hydraulic testing machine. We applied a mean load of 250 Newton, amplitude 200 Newton, maximum load then 450 Newton, frequency 20 Hertz. This here is the crack propagation rate, and the crack length then at the overload was 1.75 millimeter of the fatigue crack. And this is how the fatigue crack looked like. Here you can see the fatigue crack growing in this notch. We calculated the plastic zone should be about 4 microns, but if we measured the plastic zone visible here by these slip lines here, then we get about 80 microns, which is much larger than calculated by linear elastic fracture mechanics from the applied load. So this is the crack tip. It's not so clearly visible. Maybe here the crack path looks a little bit comparable to what we had in the last presentation. And on the fracture surface, you find these nice striations at the beginning, in the middle, and at the end of the fatigue crack. And this is after the overload. This happened by accident. And yeah, this is the plastic zone. You have a huge plastic zone. You have a widely open crack. This here is the total plastic zone, nicely visible by the slip lines here in front. And if you compare it, what you find in literature, it looks more like the plastic zone in a plane stressed state. And this here in our steel was more like this, plastic zone bean or kidney in the plane strain state. This is what we found. And here, the crack tip, you see this bifurcation of the crack. And this is also what you find in one of the 4 papers about the overload. Is what exactly what we have done actually. And the reason here, which is given why you have a deceleration of the crack propagation, is the bifurcation, as you can see here. But if we then continue our crack propagation, the crack growth was not decelerated. After the overload, the plastic zone size of the cyclic loading was 250 microns. 80 microns was it before the overload, and the crack propagation rate increased. So the completely different effect as in the normal metal was found. And this we also investigated on a second specimen here, and here there were 2 times an overload, and this is just the potential of the potential drop measurements and the number of cycles, and you see that there is no deceleration found. Yes, and therefore the overload in bulk metallic classes is not investigated so far, but it looks interesting because the effect is completely different what we know from normal metals, and what we also think it's quite easy to investigate because we see the plastic zone so clearly, so it may be a good model material. So thank you for your attention.
Yeah.